Suppose we want to do a reflection of a vector x across a hyperplane, so here in red, to get the vector x prime, such that x prime has as first component the norm of x and as other components 0. We can use a Hausdorff transformation to do so. Okay. First, notice that the vector u, which goes from x prime to x, can be expressed obviously as x minus x prime. Okay, x prime plus u equal x, so obviously u equals x minus x prime. Then notice that half of the vector u can be given by the projection of x onto the axis spanned by the vector u. Okay, notice that here. First, what you want to do is to normalize u, okay, to get the unit vector v, okay, here. So we do so by dividing the vector u by its length, or by its norm, okay. So v equals u divided by its norm, okay. Now, to get the projection of x onto the axis spanned by u and by also the unit vector v, we can simply take the dot product of x and v, okay. So we take the dot product of x and v. Because remember, the dot product gives us the projection of one vector onto the axis spanned by the other vector if the other vector is a unit vector, okay? Which is the case here for v, okay? Remember that. And we can write that in matrix form as v transpose x, okay? The dot product of v and x can be written in matrix form as v transpose x, okay? Remember that. Now, remember that v is given by u divided by its length. So, the dot product of v and x, so v transpose x, can be also expressed as u transpose x divided by the norm of u. Okay, it's just the same thing. Now, coming back to our reflection. Remember that our vector x reflected, so x prime, okay, is given by x minus u, okay? We go from x, here we start from x, and we go to x prime, and to do so we pass by, we take the negative of the vector u, okay? And this vector u can be expressed, as said before, as half of the vector u here is given by the projection of x onto the axis spanned by the unit vector v, okay? So if we take it 2 times, you get the entire vector u, okay? That's what's written here, okay? So u is 2 times the dot product of v and x, okay? So the projection of x onto the axis spanned by the vector v. And we multiply by v here because we want to give it a direction, okay? Remember that the result of the dot product of 2 vectors doesn't have any direction. It's just a scalar or a magnitude. We multiply by v, so we are on the axis spanned by the vector v, okay? That's what we want. So x prime is x minus 2 times v transpose x, okay? Or x prime is x minus 2 times the projection of x onto the axis spanned by the unit vector v, okay? Now we can rewrite that, okay, as x minus 2 times u transpose x over divided by the norm of u times the norm of u, okay? And this can be written as x minus 2 times u transpose x divided by the norm squared, okay? All I did is replace v by u divided by its length, okay? And I did the same thing, of course, for v transpose, okay? Which also needs to be divided by the norm of u, obviously, okay? Now, remember that the norm squared of a vector is simply the dot product, okay? Which can again be expressed in matrix form. So the norm of u squared is simply equal to u transpose u, okay? So now, our reflection, which gives us the vector x prime, okay? Remember, the first component of the vector x prime is simply the norm of x, and all those are as 0. To get x prime is simply h times x, okay, where we call h the Householder transformation, and that h times x is simply x minus 2 times u transpose x over u transpose u, okay, that comes from what we said before. And so now we can factor out the x, and so we get that h times x is x times, in parentheses, the identity matrix minus u times u transpose over u transpose u. Okay, remember that u transpose u is the dot product, which is the norm squared. Okay, because we need to divide both u, both u and u transpose by the norm to get the unit vector. And remember basically that the v transpose, basically we associate it with the x to get the dot product, okay? And we have a v here to indicate the direction, because remember that the result of the dot product of two vectors doesn't give any direction, okay? So our Householder transformation H is equal to the identity matrix minus u times u transpose over u transpose u, okay? And u is given by x minus x prime, okay, where x prime is, again, has as first component the length of x, of our original vector x, okay, here, and all other components are 0, okay? And so that is the Householder transformation that we want. And generally, we use the Householder transformation to do a QR decomposition of a matrix. Okay, so A equals QR, and Q transpose A equals R. Okay, because Q is orthogonal, orthonormal. And notice that if we apply several Householder transformations on A, we finally should get a per triangle matrix R. So given that Q transpose A equals to R and that all our Householder transformations applied to A also give R, Q transpose is equal to the product of all those successive Householder transformations, and so Q is equal to the transpose of the product of all our Householder transformations, okay? So Q is equal to the transpose of Hi until the product of H1 until Hi, and so this is equal to H1 transpose until Hi transpose, okay? If you remember matrix multiplication rules and the transpose of matrix multiplication rules, okay? So generally what you will do to do a QR decomposition of a matrix using the Householder transformation is first we consider the entire matrix A, okay? And we especially will need the first column vector of it, okay? We use this first column vector to get our vector u here, okay? By having where x is the first column vector and x prime has the norm of the first column vector as first component and 0 elsewhere, okay? So we get the vector u, then we plug it into our formula to get our Householder transformation, and then we apply it, to A, okay? So this is our first Householder transformation. Then we will consider the sub-matrix. I hope you can see it. Wait a second. Wait a second, just so. I hope you can still see it. We consider the the first submatrix of A, okay? Because remember what you want is an upper triangle matrix. So by the first column vector here, only the first component will be non-zero. But by the second one, the first one and the second one will be non-zero. So to do that, we only consider basically the column vector without the first element of this column vector. So without this one, okay? So we can again do our Householder transformation and get one non-zero component, which will be the second component, okay? I hope you understand what I say. So to do so, we consider the submatrix. So suppose here A is a 4x4 matrix. So I said our first Haushalter transformation will be a 4x4 matrix, but then our second one will be a 3x3 matrix, okay, if we consider the submatrix. So we again apply the formula by using again the column vector of the first submatrix as to get U, but then we will fill in one row and one column with the 1 in the diagonal and the 0 elsewhere to again get a 4x4 matrix, okay? So we can again multiply A, basically A times H1, okay? The result of that, which is again a 4x4 matrix. We will multiply that result by our Haushalter transformation H2, and as said, we put the 1 in the diagonal and 0 elsewhere to get again a 4x4 matrix, and we put our Haushalter transformation of the submatrix in the place of the submatrix, okay? Then we get again a result which will be a 4x4 matrix again, and then we will consider the submatrix, okay? Which this time, if A was originally a 4x4 matrix, the second submatrix will be a 2x2 matrix, okay? So H3. Again, we will our Haushalter transformation will be originally a 2x2 matrix because we consider the submatrix, okay? Again, where we will use the column vector of this submatrix, the first column vector of this submatrix to get our vector U, okay, and to find our Haushalter transformation, and then we will put 2 1s in the diagonal and 0 elsewhere to again get a 4x4 matrix, where we can again multiply it by A, respectively by A times H1 times H2, okay? And then we will finally get an upper triangle matrix, okay? Generally, once you've reached the 2x2 submatrix, you stop, because, yeah, I said you want the upper triangle matrix, so yeah, you need to stop by a 2x2 submatrix, okay? And I think that's it, okay? So basically, here is the derivation of how you come on that strange Haushalter formula. Okay, so basically it's just a reflection in such a way that the reflected vector has the length of the original vector as first component and 0 elsewhere, and from that you can use the properties of the dot product and the matrix notation to rearrange into your Haushalter formula. And we generally use the Haushalter transformation to do a QR decomposition of a matrix. As said, if you apply all your Haushalter transformation until the 2x2 submatrix, you get an upper triangle matrix, okay? And which will be your R, and all these successive Haushalter transformations, they will give you Q transpose, so Q will be equal to the transpose of all those successive Haushalter transformation, okay? And to proceed again, you consider your entire matrix, and you consider especially the first column vector of this matrix, so you can compute your vector U, which you will need in your Haushalter formula. Okay, then you consider the submatrix, okay, and you consider the first column vector of this submatrix, and you do the same thing. You compute your U and you plug that into your formula, and then you put a 1 in the diagonal to get the same number of dimensions as A, as the result of A times your first Haushalter transformations, and 0 elsewhere, okay? And then you proceed, you continue until you get 2x2 submatrix, okay? Yes, I hope this is clear, and I will do a few examples, some examples in the next few videos.